I welcome everyone to this session. My name is Siva Marimuthu. I am working as a senior lecturer at Nilai University, Malaysia. Today we are going to discuss about applications of biomimetics in aerospace. Okay, let's see the meaning of the biomimetic is a combination of two words, bio and mimetic. Bio means biology and mimetic means copying. Mimetic can also be called as mimic. So this biomimetic can also be called as biomimicry. So literally we are going to copy the solutions from nature to solve the problems in the engineering sciences. Today in particular we are going to see the problems that have been solved in aerospace with the help of the solutions taken from the biological environment. It is not a new thing. It is not started today, or it is not started within a decade, and it's been practiced since 16th century. And if you see, the perfect example for the use of biomimetic solutions from nature is the sketch of ornithopter, which was drawn by Leonardo da Vinci. And if you see the sketch on the screen, I hope you all can able to see the sketch on the screen. So this sketch is a perfect replication of a bird. So Leonardo da Vinci was curious about the way the birds were flying, and he coined this sketch. It is a fundamental idea behind the aircraft flight. So this all started the earlier 16th century. To be more precise, it is sketched around 1505. So this is what called as biomimetic. So copying the solutions from the nature to address or to solve the problems in the engineering sciences. Okay, let's go to the next slide. I will give you a brief introduction about the topic. As I was saying, biomimetic is a way of finding solutions to the practical problems of engineering sciences from nature. So how the solutions are implemented? The solutions are not implemented same way as how you see the solutions on the biological environment. The way it is implemented is entirely different in the field of engineering sciences. So that's a very big challenge to all the researchers even today. And let's continue some of the biological solutions that's been taken into account. For example, Otto Lilienthal. I hope you can able to remember Otto Lilienthal. He is also called as Flying Man, and he was the first person who designed a glider and also who flew successfully in a glider. You know, a glider is an unpowered flight, and Otto Lilienthal and his brother Gusto, they were observing the stork birds. I hope you can able to see the picture of the stork birds, and they predicted the way the birds flock their wings and the pathway followed by the stork. So this stork wings gave them an impression about a man-made flight, and they came up with an idea of a glider without any propeller, hence it is called as a glider. And Otto Lilienthal himself flew successfully, and you can see the picture of Otto Lilienthal from the top hill to the downhill, and this was the first recorded glide flight, and it happened in the later 19th century, and it was followed by Frederick William Lanchester, who is also called as father of British aeronautics. He gave the design of fuselage based on the structure of seagulls. I hope you can able to see the picture of seagull. One day he was wondering about the way seagull was flying over the American oceans, and he came up with an idea of fuselage structure, and he made the fuselage structures on rainbow trout. A rainbow trout is nothing but it's a kind of fish. Rainbow, you know, that mixture of colors. The way the fish looks is mostly like a rainbow mixture of colors, hence it is called as rainbow trout. And this aircraft fuselage design was made on the rainbow trout, and it was done by the father of British aeronautics, who is also called as F.W. Lanchester. Let's move to the next slide. The overview of today's discussion is all about drag reduction, effective control, and strength, noise reduction, and safe landing. So we are going to discuss about the kind of materials or the ideas that's been taken from the biological environment to solve the problems in the aircraft. So we will discuss further. We will start from drag reduction. Winglets are these structures used on the wingtips to reduce drag. This is a replication of eagle winglets. When you see the eagle wing on the screen, one side of the eagle wing has a larger amount of wingtip vertices. On the other side, it has a smaller amount of wingtip vertices. The reason between the different concentration of wingtip vertices is because of the flat surfaced wing and the curled up surfaced wing. And when you see the wingtip vertices on a flat surfaced wing, the amount of concentration of the wingtip vertices on the span of the wing is really high. So this will greatly affect the lift generation. On the other side, the tip of the wing is curled up a little, and this literally lift off the wingtip vertices from the main surface of the wing, and also it contains the wingtip vertices within a specific boundary, and this greatly helps the eagle wing to generate more lift by reducing the drag of the wing drag due to the wingtip vertices. And this concept is called as maximum lift with minimum length by curling up. This curling up is the winglet concept which been applied onto the Boeing aircrafts. Although we are going to add a extra structure additional to the main wingspan, still the length of the wings should be kept within the limits set by the airports. For an example, Airbus 380 has a wingspan of 80 meter, and Airbus 320 has a wingspan of around 36 meters, and this should not be violated. So this limit should be kept as per the specifications, because the parking area and the runway area on the airports be designed based on these things. And when you see the picture at the bottom, I hope you can able to see it's a pathway from Heathrow, London Heathrow Airport to the Halifax Airport in Canada. The distance would be around 4,500 kilometers. Let's say you are filling a fuel of a jumbo aircraft like Airbus 380, and on average you need to spend around 20,000 US dollars to completely fill Airbus 380 for one flight. And if you can able to reduce the 3% of fuel, okay, that's a greater profit to the company. So this winglet will help you to reduce the fuel by 3%, and that will be a profit to the company. Let's see the next. Sharklet is a concept very similar to winglet. The only difference between sharklet and winglet is winglet you can see it on Boeing aircrafts, and sharklet you can see it on the Airbus aircraft. When you see this picture of Airbus 320, at the tip of the wings you can see the sharklet which is of 8 feet high at on the both the sides of the wing. So this also will help you to reduce the drag on the wing surfaces, and will help you to increase the performance of the aircraft between 3 to 4%, which is very close to the winglet. Let's take Airbus 320 as an example. Okay, it will add additionally 100 nautical miles range or increased payload capability of up to 454 kilograms, which is equivalent to 1000 pounds. And when you see this picture at the bottom, the flat surfaced wing, at the tip of the flat surfaced wing, the wingtip vertices creates, and this will greatly affect the amount of lift generation. On the other side, if the sharklet been implemented at the wingtip, it lifts off the wingtip from the surface of the wing, and also the concentration is really smaller than the previous one. So that is how the performance of the Airbus aircraft has been improved with the help of the sharklet, which is very similar to the winglet. Let's see the next. Drag reduction is the implementation of shark skin rod riblet coating, and this is a technique which was observed on the sharks. And as we all know, sharks are very famous for its fastest swimming capability in water. The main reason for this capability is because of the peculiar skin pattern on the shark. We call this one as a riblet. When you see the shark skin through a microscope, you could possibly find a denticle or a riblet pattern like this. The pattern will be little different in different shark families, and the main reason Why we are discussing about this triplet pattern is because the sharks can able to swim fastly in water due to reduction in turbulence. The turbulence is greatly reduced in the flow because of the arrangement of this riblet pattern on the shark skin surfaces. This riblet patches are applied onto the fuselage and wings that mimic the effect of shark skin. Of course, if you see a new Airbus 350 XWB aircraft, these shark skin coatings are already applied on the aft fuselage and also on the surface of the wing. This greatly reduced the drag on the fuselage and on the wings, and it increased the performance of the aircraft in high-speed cruise flight. So this is a better example of drag reduction, and it is in practical use right now. So this is the end of drag reduction. Next we will discuss about the effective control. So how the problems in the aircraft stability and control has been addressed and solved with the help of the biomimetic idea. A sudden wind with high turbulence is called as gust wind. In simple words, it's a disturbance in the fluid flow. This disturbance been tackled very cleverly in the peregrine falcon. When you see a peregrine falcon bird, the beak of the peregrine falcon has the capability to sense the gust wind at further distances. Once it senses the approach of gust wind, it passes the signals to the wings. The shape of the wings will get changes accordingly to the current of the gust wind. So this methodology has been observed and taken onto the aircraft and implemented with the help of flaps and slats. Flaps and slats are the control surfaces, and when you see a new Airbus 350 XWB aircraft, the nose of the Airbus 350 aircraft has the probes which senses the approach of gust winds, which is very similar to the uh, beak of a peregrine falcon. And once the signals are sensed, the signals will be passed through the electrical systems to the wings. This wings is made of a morphing structure capability. You know what is morphing? Morphing means the capability to convert and transform itself. This signal, once it is received on the surface of the wing, the angle of attack of the wing, the structure of the wing will get modified a little to make use of the current as much as possible. The gust wind will be used effectively with the help of this kind of morphing wings, and it helps the Airbus 350 XWB to fly 280 miles further using the same amount of fuel. Another amazing solution in the biological environment to the problems of the group flying is the V formation flying that you could possibly identify on migrating birds. Birds used to migrate from one place to another for about 1,000 kilometers or even more. It needs to save a lot of energy before reaching destination. The way it flies, it put itself in the best possible position to make use of the upwash generated by the bird in the front. Let's consider this group. In this group, the bird at the front will create an upward air force. This upward air force will be used effectively by the bird which is flying at the aft, and this will be continued until the end of the group. And this effective use of air current by keeping the wingtips very close to each other makes the V formation flying a successful one, especially in migrating birds. The birds time their wing flaps to catch the upwash. The wingtip of a bird following another takes the same path as one in the front. This idea has already been implemented on military flying. Okay, you can see the picture of a V formation flying, which is very close to the V formation flying of a bird, but it is not applied to the passenger aircraft because of the safety reasons. Next, we are going to discuss about the ways to control effectively the wings with high aspect ratio. Generally, it is really hard to control an aircraft wing with high aspect ratio. Aspect ratio is the ratio between the span and the chord, or the span and the wing area. We can define it by many means. But however, although it is very hard in real time, albatross, a seafaring bird, effectively control the wing with high aspect ratio. Still, Airbus engineers are studying deeply about this concept, and although the Airbus 320 got lesser aspect ratio than Albatross, still the bird managed to control the wings very effectively. So this idea, when I hope if we can able to predict the ways it can able to control the aspect ratio wing, high aspect ratio wing more effectively, that would help us more in maintaining the stability of the aircraft. Next, we are going to discuss about improving the quality of the flight. Okay, we are going to discuss about the Dragonfly aircraft. When you see the top view of a Dragonfly aircraft, you can see a forward swept wing and a backward swept, or more close to a delta wing. The main feature of this Dragonfly aircraft is that it can able to generate a leading edge spiral vortex, which is analog to the flow generator, which gives more stability to the flight. So that particular ideology has been taken into account to develop this Dragonfly aircraft. This is a 3D design of a Dragonfly aircraft, and it has a canard wing at the front and a forward swept wing at the aft. It is a mixture of Grumman X-29 and Superman Spitfire, and this combination effectively showed good result in terms of maintaining stability. Another stability issue that need to be addressed is the auto rotation in microaerial vehicles, simply called as MAV. Natural Samira, it's a kind of insect. It can able to perform a stable auto rotation during descent. This methodology has been considered to solve the auto rotation issues in the monowing micro aircraft. When you see this picture on the screen, which has only one wing, hence it is called as a monowing. At the tip of the wing, it has a tail rotor. A tail rotor is normally used to fight the torque generated by the main rotor in terms of helicopter, but here in this micro aerial vehicle it is used in opposite way. The propulsive section maintains rotation to allow it to hover. Here the propulsive section refers to the tail rotor. So this solves the problem of instability and makes the monowing micro aircraft more stable. Next, we are going to discuss about the uh, available solutions in nature to improve the strength of materials. The load carrying capacity of an Airbus aircraft has been improved with the help of an Airbus Beluga design. This Airbus Beluga design is a simple replication of an beluga whale. If you see the head and the fuselage structure, you can easily identify the similarities between the Airbus Beluga aircraft and the beluga whale. In the Airbus design, now the cockpit has been moved to the bottom, which gives us more easy way to access the cargo compartment of the Airbus Beluga. We can able to load or unload the equipments into the Airbus Beluga through the front door. So this section will be used as a front door. So this is more effective than the previous versions of Airbus. Without having to disconnect any electrical or hydraulic or flight control connections, we can able to simply load or unload the components. So the Airbus 300 to 600 Super Transporter Beluga series, the payload was more than double, which was increased more than doubled, and the volume increased by more than 30%, and which is good to the company. It will earn more, and the loading times were reportedly halved when compared to Super Guppy. Super Guppy is a competitive model to this Airbus, and Super Guppy is a Boeing model. The main deck cargo volume of the Beluga is greater than that of C5 Galaxy or the Antonov AN-25, but it is still lesser than the Antonov 225. So this capacity of load increased capacity of cargo carrying is an enormous improvement in the load carrying capacity of an Airbus design. The next big challenge is to increase the load carrying capacity of a spoiler. When you see a Victoria water lily, also called as Victoria amazonica, it has superior ability to support significant point loads. When you see a 3D printed Victoria water lily which is floating on the water, could possibly carry the weight of a child, it is very impressive. The plant's leaf vine structure provides a model for reinforcing surfaces that supports too many loads. It is still under developmental stage. Engineers in Airbus developed the inner surface of a 3D printed aircraft spoiler with Victoria water lily and drawn up as a part of the concept study, and hope this will be implemented in the future in a real spoiler of an aircraft. Next, we will discuss about the ways to reduce the noise in aircraft with the help of the solutions from nature. The noises generated by the aircraft wings can be reduced with the help of the owls. When you see an owl, it can able to fly very quietly in air because it got much finer feather than any other ordinary birds. And when you see the texture of this wing, it has a peculiar pattern. It has a trailing edge fringe, velvety down, and a leading edge comb. These three combination you could identify only on wings of owl. You cannot able to identify in any other birds. So this combination enabled the bird to fly quietly in air. Researchers did too many researches and they came up with a device that you could bolt onto the trailing edge of an aircraft wing or a wind turbine to reduce the noise level. And this is under developmental stage. They successfully tested this device in wind tunnel. Continuing with all wings, here we are going to discuss about reducing the noise at the time of landing in aircrafts. Owls' downy leg feathers enable the owls to descend almost noiselessly on their unsuspecting prey. Because of this velvety down leg feathers, researchers are attempting to replicate this velvety coating on a landing gear to reduce the landing gear's noise at the time of takeoff and landing. Not only the owl's texture enable the noise reduction, the very structure of owl created a greater attraction. When you see the side view of an owl and a side view of a B2 spirit, it is more close. The way the B2 spirit been designed, okay, it's a simple replication of an owl which helps the B2 spirit to reduce the noise as much as possible. So it is another example to reduce the noise. The last section of today's topic will be the safe landing. Many researches has been carried out to reduce the shocks in the shock absorption system. However, the solutions are already available in nature. When you see a woodpecker hits the wood with its beak for about 18 to 22 times per second with a deceleration of 1200 gravitational force. It is really amazing. Although it is hitting at a very faster rate, there is no signs of crack or damage anywhere in any part of the body of the woodpecker. It is because of the effective handling of shock absorbing mechanism in its nature. It is done with the help of the four combination of layers. One is an external layer, which is a very hard one, and example woodpecker's beak. And the second one is a viscoelastic layer, so which will distribute the vibrations to the other layers, and here it is done with the help of a hyoid bone. And the third one is a porous structure, will try to suppress the vibrations. Here it is done with the help of a spongy bone and another high strengthy layer, and this is highly porous and it will not allow the vibration to spread further. So it is done with the help of a skull bone. These four combinations of bones in the nature of woodpecker enable the woodpecker to effectively control the shock. So this shock absorption system can be implemented in landing gears to effectively control the shocks. Hopefully it will be implemented in future. It will be very effective to control the G-force tolerance of micro machine devices in the shock absorption system. Next, we are going to discuss about the ways to improve the visibility at the time of landing in unmanned aerial vehicles. Landing is a crucial part in unmanned aerial vehicles. Let's take bees for an example. When bees approaches the target where it's supposed to land, the surface they are approaching expands at a constant rate within their field of vision. This enables the bees to land precisely on the target. This approach can be utilized to improve the landing safety of an unmanned aerial vehicle. So far, we discussed about the problems in aerospace and the ways to solve from the biological environment. But biomimetic is not only limited to aerospace, it's been applied in many fields. Let's take automobile industry as an example. The best example I can give you right now is the Shinkansen bullet train. This Japanese bullet train, when it was designed at first, the nose was really blunt, and the scientist had difficulties in to make this train to run through the tunnels. When it approaches the tunnels, it created big shock waves, and the passengers who were seated inside the trains felt shrinking, and this really affected the speed of the bullet train. Finally, the researchers came up with the idea that they noticed on the kingfisher bird. If you see the beak of the kingfisher bird, which is really long, and this enable the kingfisher bird to catch the prey from water without inducing any kind of waves. So this methodology has been replicated to improve the nose of the Shinkansen bullet train. Now if you see the picture of the bullet train, it is long at around 13 meter, and now it can able to run through tunnels without creating any waves, and the speed is also as high as 330 miles per hour. Moreover, the pressure has been reduced by 30% and fuel has been reduced a lot. So this is how the biomimetics is implemented everywhere. As I was saying, biomimetics are used to solve many practical problems in civil, mechanical, automobile, marine engineering, and so on. Although we have identified many ideas from nature which could possibly fix several issues in engineering sciences, it is really challenging to replicate or mimic. For an example, Victoria Lily still it is under conceptual stage. The noise reduction with the help of the owl wings texture, it is under developmental stage. So there are too many difficulties which is faced by the industrialists and researchers. They are all still working together hardly to bring those bio-inspired ideas into existence. Companies like Airbus has launched several projects inspired by biological systems and methods in order to develop new technical solutions. This collective idea would give a new definition to aerospace evaluation. And the famous biomimetic researcher Wood says nature is a mentor, which means there are still too many solutions available to the practical problems of engineering sciences. We need to find it. And the better example I can give you for the biomimetic implementation to the conventional problems of aircraft is the new model of Airbus 350 XWB, which got too many biomimetic applications like the shortlet, the nose probe, or the short riblet coating. So likewise, it has too many biomimetic applications, and this is a better example for the implementation of biomimetics in aerospace. For more details, refer Biomimetics in Turbulence Reduction Recent Developments or asknature.org, which got collection of biomimetic applications, and airbus.com for the recent development in Airbus with respect to the bio-inspired theme. And you can also write to me at Marimuthu at nilai.edu.my for any queries. I thank all the viewers for attending this presentation. I hope you got an idea about biomimetics in aerospace. Thank you everyone.